Hello everyone, and welcome to this webinar on real-time simulation for de-risking energy storage integration. Thank you for joining us for another RTDS Technologies webinar. My name is Katie Sidwell, and I'm joined today by my colleague, Ani Nzimako. I'm going to begin today by giving a brief presentation with some background information on the history of real-time simulation and the advantages of this type of technology, the hardware and software that is required to carry out these studies, and a couple of general considerations for modeling energy storage. And then Ani will take over and present specifically on energy storage technologies and how we model them with the RTDS simulator, and then she'll give a screen share demo in the Rscad software and show you a real-time energy storage simulation. We will have a Q&A session after the demo, and we encourage you to submit your questions via the Q&A module. We will be answering them via text throughout the presentations and then addressing some in the live Q&A. As always, please say hello in the chat and introduce yourself. Let us know where you're joining us from. It's great to see familiar and new faces here. We will also be distributing a recording of the webinar and a Q&A document after the event, and we'll distribute that via email to all of the registrants. So you'll receive the slides, the recording, and the Q&A automatically, so don't worry about that. All right, let's get into some real-time simulation fundamentals. So if you're not familiar with our company, RTDS Technologies is based in Winnipeg, Manitoba, which is a research hub for HVDC technology in Canada and on the world stage as well. We pioneered real-time simulation for the power industry in the 1980s by creating our technology, the RTDS Simulator. Before the emergence of real-time simulation, the main way of testing HVDC controls in the laboratory prior to deployment was by using analog simulators. These were essentially scaled-down physical models of the network of interest that could then be connected to the control cubicles for the HVDC project to test their dynamic performance, for example, and to ensure they were functioning as expected through a wide range of conditions. Here we can see the control room for a huge analog simulator. These were very expensive, massive, and more significantly, they were very inflexible. So it could take weeks or months to reconfigure the analog components for a particular study. So there was a need for a much more flexible method, and that was really the motivation for developing a digital, computer-based solution. So real-time digital power system simulation was originally born out of necessity for the ability to test HVDC controls in a convenient and flexible way. And the research project that gave rise to the development of the world's first real-time simulator took place at the Manitoba HVDC Research Center. You might know it as the home of the Rscad software. And the developers branched out and created RTDS Technologies, the company. Today, the RTDS simulator has users in over 50 countries. We have four main categories of user. There are electric utilities, power system protection and control manufacturers, research and learning institutions, and consultants. So here's a look at just some of the utilities worldwide who are RTDS simulator users. The applications here are quite varied, from utilities who operate HVDC links and use the real-time simulator to test replica controls, to those developing and testing special protection systems, cybersecurity laboratories, microgrids. There's quite a lot out there. And looking here at some manufacturing and some research and educational users, all of the major manufacturers of power system protection and control equipment are users of the RTDS simulator. So this is just a subset of our customer base in that area. These institutions like Siemens, ABB, and SEL have really integrated hardware-in-the-loop testing into the factory acceptance testing of their HVDC and protection equipment. And more, we're seeing hardware-in-the-loop factory testing from the manufacturer side applied to distribution automation and control equipment, like power plant controllers, for example, which might be involved with energy storage projects. And we also have well over 200 research and educational customers worldwide, a few of which are shown here. There are diverse opportunities to apply this technology, and we've seen a huge array of application areas develop over the last several years, particularly relating to distributed energy. We don't have time to touch on them today as we're focused on energy storage, but we have a wealth of information and technical papers in all of these areas, so please reach out to us or visit our website if you have questions about a particular use case. So the RTDS Simulator and Rscad software do electromagnetic transient or EMT simulation, and different types of power system simulation are required at different project stages or to meet different requirements. So load flow and transient stability analysis, for example, give you phasors around the fundamental frequency as an output, whereas EMT simulation provides a time-varying, instantaneous value output, a waveform like the one shown here that would match the current or voltage waveform if it were to be measured from the real system. So this is quite different from an RMS simulation. This allows for a greater depth of analysis over a wide frequency range and the ability to reproduce fast transients on the power system. And the higher the sampling frequency of the simulation, the higher frequency results you can accurately reproduce. The period of the sampling frequency, or the distance between two consecutive simulation outputs, is called the time step, or delta t as shown here. And the typical time step for the RTDS simulator is in the 25 to 50 microsecond range. But if we want to represent the high frequency switching of power electronics, for example, for simulating converters for interfacing a battery to the grid, we need to use a smaller time step, closer to the 1 to 3 microsecond range, typically. And all of these time steps are possible with the RTDS simulator, and you'll see that in the demo. So why EMT simulation? For steady state analysis, RMS or phasor solutions provide satisfactory results, and they've traditionally been the most widely used type of model from a power systems planning and operations perspective. That being said, existing technical codes are geared toward conventional grids dominated by rotating machines, and with the modern system and its increasing share of power electronics-based assets, like battery storage systems, for example, we come across some issues. RMS simulation lacks the ability to represent low-level controls of inverter-based systems and to capture subcycle phenomena associated with transients. So we've seen increasing evidence that for systems with a high penetration of converter-based generation, phasor simulation provides results that are too optimistic. EMT simulation will be increasingly necessary for system studies as it provides more realistic results and it's more likely to reliably predict things like control instability. What does it mean to operate in real time? When we say real time, we mean the computer needs to solve all of the equations for the network in real-world time equal to or less than the simulation time step. And this means that the real time for a power system event to occur is equal to the simulated time. Offline EMT simulation programs run on standard PCs rather than using dedicated parallel processing hardware, so the time they need to complete these simulations is typically much greater. And that's one of the advantages of real-time simulation: efficiency. But beyond efficiency, the principal advantage of running simulations in real time is the ability to connect external hardware to the simulation and test it in a closed loop. Closing the loop means not only observing the response of a protection or control device to an imposed signal, but also interfacing that response back into the simulated network. And that's called hardware in the loop testing. It's only possible if we are updating the inputs and the outputs of our simulation continuously in real time. It's not possible with non-real-time modeling tools or with open-loop testing tools like a relay test set, for example. And those open-loop tools lack the flexibility to test multiple devices at once or to allow for detailed modeling of the network, for example, including power electronics. So it's very valuable for engineers to be able to test interoperability and interactions between different systems with real physical devices. Unfortunately, the complexity of systems with distributed energy and bidirectional power flow in distribution networks means that standard modeling and test practices can be blind to vulnerabilities in the system. So being able to reliably predict instabilities and other issues is the real value of HIL testing. To do nodal analysis on the power system with a 50 or 25 or 1 microsecond time step is very computationally intensive. And of course, the processing power required increases with the size and complexity of the network that you want to simulate. So to achieve this, the RTDS simulator is built on dedicated parallel processing hardware. Our current hardware generation is based on IBM's Power 8 multi-core processor, and we've developed it at the embedded level. So there's no underlying operating system. We run our executable code bare metal for higher efficiency. And we achieve modularity through core licensing. So the quantity of cores licensed on a given unit determines the size and complexity of the simulation it can run. There is a link between the user's PC running our software and the simulation hardware. So when you watch the demo, you'll be seeing Ani's view of the graphical user interface on her PC, but you won't see the actual simulation hardware at our headquarters, which is carrying out the simulation and running the executable code. In order to connect the simulation to external equipment and realize our closed loop, we use input and output cards which are connected to the simulation hardware via a fiber cable. And the I/O can be based on communication protocols or more traditional I/O involving analog and digital signals. So for example, you might send system voltage and current or real and reactive power values for distributed energy resources from the simulated system to the physical device under test, and you could do that using analog quantities via our analog output card or using a protocol like DNP3. And you may wish to send breaker commands from the device under test using our digital input card or with a protocol like IEC 61850 Goose. Now that we've discussed the hardware interface, focusing on the software aspect of the tool. Rscad is our proprietary software, and it allows you to configure your circuit model and interact with the simulation. So here you can see the draft module where the user builds their circuit and enters parameters into the models. You'll see it in much more detail in the demo, as well as the operator's console where the user can apply contingencies to the system and change parameters in real time. Recently, we released a new and improved version of the software called Rscad Fx, so we've updated the look and feel of the GUI and added quite a few features to increase productivity and improve ease of use for users. So obviously, if you're totally new to Rscad, you won't see the difference, but if you've seen older versions, you'll notice in our demo today, we're using the new version of the GUI, so you'll get to see how that looks. The Rscad component library has several options for energy storage modeling. We have a PEM-type fuel cell component with inputs of cell temperature and anode-cathode pressure. We have a lithium-ion battery model that will be used today, and the focus of this model is the electrical behavior of the battery. It's not a chemical model. We do accept temperature as an input and use interpolation to calculate the internal parameters according to the temperature and state of charge. We have mechanical energy storage modeling options as well, namely Flywheel and pumped hydro storage, and Rscad comes with fully documented sample cases for both of those, including the controls and of course the power electronics modeling. Today, Ani is going to demonstrate a microgrid case that contains both a battery and a flywheel, and she'll also show you the pumped storage sample case, all with detailed power electronics and controls internal to the case. But the idea is that you could potentially take those controls and move them outside of the simulation, have them on physical devices, and test those devices in a loop with the energy storage system model. Modeling power electronic converters is obviously an important part of representing energy storage systems. Ani will go into more details about our available converter models, but it's important to remember that our power electronics run on the central RTDS simulator hardware, the multi-core processor, so there's no need to use an external FPGA. Typically, you'd have the AC network run on one core in the main step environment, for example, at a time step of 30 microseconds, and power electronics would be simulated in our substep environment on a separate core interfaced to the AC network at a fraction of that main time step, for example, 3 microseconds. And running at that lower time step means you can run what we call a fully switched model, representing the high frequency switching dynamics of the converter. However, that level of detail isn't always required by the user, And for that reason, we have average value models, which still accurately represent the power profile of the converter in transient conditions, but they do so in the main time step environment without representing those switching dynamics. And these models are much lighter computationally speaking, which is an advantage. We also have a really exciting new converter modeling option called the Universal Converter Model, or UCM, and this is a switching function state space model. The huge advantage of this model is that it can accurately represent switching in the 3 kHz range in the main time step environment at a relatively relaxed time step, say 30 to 50 microseconds. And that's really going to change what RTDS Simulator users can do, power electronics-wise, with a limited quantity of simulation hardware. It also has a very high performance in the sub-step environment, accurately switching at over 100 kHz. So next month, we will be having a webinar to introduce this model and to get into the details of how it works and all the advantages. So you don't want to miss that webinar. It's on June 30th, and you can register on our website. I wanted to mention one practical example of an energy storage project using the RTDS simulator. San Diego Gas and Electric, a utility in the US, has done some work in establishing a hardware-in-the-loop testbed for battery system integration onto their network. So here, their RTDS simulator represents the battery itself and its converter, and a small portion of the surrounding network. They can connect a replica of their distributed energy resource management system, their DERMS, to the simulation to validate the functional behavior of the third-party battery control and see how it interacts with their higher level control system. And here they're also studying the effects of the new control on local protection by including physical protective relays in the loop. So this really shows the value of a real-time simulator in the context of energy storage. You can connect multiple hardware or software devices in the loop with the simulated network and test interaction and system level coordination with real hardware. So I think this type of study will become more and more common for utilities who are struggling to manage the large-scale integration of storage elements. All right, thank you for your attention. I'll turn it now over to Ani for her presentation and demo.
Hello everyone. So an introduction to energy storage systems. There are now challenges associated with pollution from fossil fuel emissions, the environmental impact of large hydroelectric dams, and the need to provide energy access to remote communities have created strong growth and demand for renewable energy. Renewable energy systems like wind and solar are intermittent in nature. Energy storage technologies are required to ensure that they can operate reliably and efficiently when they're connected to existing grids or in standalone remote communities. Several types of energy storage systems include mechanical, like pumped hydro storage, combustion engines, and flywheels; electrochemical energy storage systems, like batteries and fuel cells; thermal energy storage systems, like molten salt, geothermal; chemical or biochemical energy storage systems, like biomass and methane. Several applications of energy storage systems include allowing the integration of solar and renewable energy sources. Energy storage systems helps to address the technical challenges related to the stability and control of variable renewables, which provide difficulties in integrating them into existing grids in a cost-effective manner. Energy storage systems are a significant resource for maximizing bulk transmission and distribution system power capacities. Energy storage systems provide fast power reserves, helps to reduce greenhouse gas reductions from bringing in fossil fuel and thermal generation plants on the grid. In traditional networks, consumers received power from large conventional generations through bulk transmission systems to distribution networks. They could not participate in grid support services. With the integration of renewable energy resources with energy storage, on-site energy storage systems allow consumers to store energy during high renewable periods and to supply that energy to the grid and generate revenue. Energy storage systems allow additional energy capacity for supporting plug-in electric vehicles and transportation. Over the last decade, energy storage technologies continue to evolve and innovate in response to this increasing energy demand. There is need for accurate simulation models to investigate, design, and test reliable power and control system solutions to address the technical challenges of integrating renewables and distributed energy resources with energy storage technologies. In this next section, we'll describe the modeling of a pumped storage system, a battery system, and a flywheel. Pumped hydro systems are the most mature and widespread method for large-scale electricity storage. Pumped hydro systems contribute over 95% of global energy storage capacity. They store and generate electricity by moving water between reservoirs located at different elevation levels. Pump hydro storage provide benefits like providing bulk energy storage for locations where large conventional hydro systems are not viable. They provide fast load and energy balancing, black start grid capability, and reactive power supports. Pump hydro storage systems have high operating efficiencies and life cycles over 50 years. Drawbacks include requiring a high capital investment, and they require the access to reliable transmission networks for power supply to the grid and the loads. To model the pump hydro storage operation, the model has to represent the generation mode, which occurs during high demand or low renewable generation. The water is moved from the upper reservoir to the lower reservoir through the turbine. The generator converts the stored potential energy in the reservoir to electrical energy and supplies the connected grid and loads. The pumping mode operation is reversed. During low demand or high renewable generation, water is moved from the lower reservoir to the upper reservoir by the pump. The motor of the pumped hydro storage units draws power from the grid to pump the water to the upper reservoir. The pump and turbine controls regulates the water flow between the reservoirs by adjusting the speed and gate position for a given water head and a set power reference. In practical applications, the transition from generation to pumping mode is performed by an operator, and this takes several minutes. It's typically not a focus of dynamic simulation studies, and in most simulation studies, the generation and the pumping mode operation can be studied separately. Modern pumped hydro storage systems use variable speed motor and generator units driven by combined pump and turbine systems. The benefits of combined pump turbine hydro units include reduced plant cost and size. The downside is that there is a longer transition period between pumping and generation modes, since the turbine blades have to fully come to a stop, change direction to switch operation modes. Variable speed units with power electronic converters provide increased reliability and flexibility by providing fast power and frequency regulation in both pumping and generation mode. There are two main configurations for variable speed units, which are the doubly fed induction units and the full converter fed synchronous machine units. In the full converter units, a synchronous machine is connected to the grid through a full power-rated back-to-back converter. The power converter can control the machine's stator magnetic field frequency from 0 to rated speed, producing substantially large torques at 0 speed, allowing the rapid startup of the pump hydro storage system. Benefits of the full converter synchronous machines include having a wide operation speed range, high efficiencies, and robustness, as well as using the well-established technology of synchronous machines. This allows existing fixed-speed synchronous machines to be retrofitted to become variable full-speed full converter units. However, due to the increased size, the cost, and the losses for using a full rated power converter, full converter synchronous machine-based pump storage units have typically been implemented for small and medium-sized applications. In doubly fed induction machine units, the stator of a wound rotor induction machine is directly connected to the grid, while the rotor is connected to the grid through a back-to-back converter. The main advantage of the doubly fed unit compared to the full converter unit is that the back-to-back converter can be rated to 30% of the rated machine power. This reduces the overall converter loss and costs, allowing the doubly fed induction machine pump storage units to be used for higher power applications. The limitations and drawbacks of the doubly fed induction machines include the use of slip rings, a low starting torque, which limits the maximum achievable rotor speed to within plus or minus 10% of the rated speed. Battery energy systems convert chemical energy to electrical energy. Common battery technologies include the lead-acid, lithium-ion, the flow batteries, and the nickel-metal batteries. There have been global cost reductions in battery technologies, allowing large-scale, high-capacity energy storage units to be used in applications such as supporting electric vehicle charging, load leveling and peak shaving resources, and the integration of renewable energy. The main components of batteries are a positive and negative electrode, which is the cathode and the anode, an electrolyte that immerses the electrodes to store and discharge the charge of the battery, as well as an insulator. Several factors determine the battery's charge and discharge operation, namely the state of charge of the battery capacity, its open circuit voltage, charge and discharge cycles, its self-discharge rates, the battery age, and the temperature dependence. In charging operation of the battery, energy is supplied to the battery cells from an external power supply. The flow of ions between the electrodes through the electrolytes allows charge to be built up in the battery. The battery operation in discharging mode, the flow of electrons moves energy through an external load, allowing the stored charge in the battery to be dissipated. The detailed modeling of the battery operating characteristics increases the complexity of the simulation model to represent the non-linear current voltage operation of the battery and its electrical parameters during charge and discharge operation. Benefits of battery systems include high energy densities, providing backup power supply for grid voltage support, flexible and customizable solution for on-site customer storage and revenue generation. Drawbacks of batteries are the high cost of startup, the maintenance, and the recycling. Batteries have limited lifespans of about 5 to 10 years, with dangerous chemicals which pose a high risk of fire hazard. Flywheel energy storage systems are fast-spinning mechanical devices that convert kinetic energy to electric energy. The kinetic energy stored in a flywheel is determined by its mass and geometry. The flywheel motor generator controls the rotation speed through a power electronic converter interface. In discharging operation, which occurs during periods of excess renewables or excess power generation, the flywheel power converter control accelerates the flywheel motor and draws electricity from the grid. In charging operation, which occurs during periods of low power generation, where the flywheel decelerates the motor to supply electrical energy to the grid. The state of energy of a flywheel defines the amount of kinetic energy that is stored or delivered during its charge or discharge period. Flywheels are typically housed in vacuum enclosures with magnetic bearings. This allows the flywheel to keep its rotation without requiring additional power for energy conservation. Flywheels can be used for fast charging of battery storage systems, uninterruptible power supplies, voltage, power, and frequency regulation for renewable energy, and in electric transportation such as ships, electric vehicles, and trains. Benefits of flywheels include the ability to provide long discharge cycles, long lifespans of 30 years, and they don't have fire and chemical hazards like batteries. The drawback is that flywheels are prone to mechanical stress and bearing failures. They require fixed installations and they are size dependent, creating space constraints. Due to the requirement for fast frequency and power regulation, modern flywheel systems use variable speed generators with fully controlled voltage source power electronic converters. The most common machine configuration used in flywheel applications are permanent magnet synchronous machines due to their low excitation losses, their low rotor design complexity, and their high efficiencies. The level of detail and accuracy required in each simulation model will be determined by the size and the type of the power system study and application. Real-time electromagnetic transient models for energy storage and renewable applications are capable to represent the power system dynamics of energy storage and renewable systems from DC to really high frequencies. For real-time digital simulation using electromagnetic transient models, a trade-off exists between the required level of detail in the simulation model, the computation speed, and the available hardware resources. To model the control systems of power electronic converters, they can be classified as grid forming or grid feeding control. In grid feeding control, the converters are can be modeled as controlled current sources. These controls require a synchronization to the grid voltage through a phase lock or frequency lock loop in order to generate and push power to the grid. The grid forming converters are modeled as voltage controlled sources. Grid forming converter controls sets the grid voltage and frequency and can allow the renewable energy resource or energy storage system to form the grid in the event of a power outage or in remote power islands. There are several characteristics that determine the modeling of control system and their operation. This includes the grid strength, the kind of load, the saturation and the grid harmonics. The control system parameters have to be selected and tuned for different operation conditions such as grid connected and islanding mode, transient faults, and the addition of more renewables and distributed generation onto the grid. The RTDS library has extensive models for generating the control systems for renewable and energy storage applications. The level of detail required to represent the power converter models used to interface renewables to the grid will be determined by the kind of study or the power system application. Converter models can be classified as switch converter models, which are the most accurate models for dynamic studies, as they represent the converter circuit for every switching state. The converter losses and switching valve currents are represented accurately in switch converter models. They require small simulation time steps used to model the high switching frequency and harmonic transients. High precision and accurate control system models are required to generate the high switching frequency firing pulses. This increases the required hardware resources and limits the number of switch converter models that can be modeled in a power system application. Switching function state space models use state space based transfer functions with internally generated switching references. They represent the switching and harmonic dynamics, as well as the converter losses, which reduce computation requirements compared to firing pulse or switch converter models. Larger simulation time steps can be used to model the converter dynamics, allowing more models to be used in the application. The control system models for generating the converter firing pulses are not required. Dynamic average converter models and dynamic PQ source models are simplified representation compared to switching function models and fully switched firing pulse converter models. They use the converter signals at fundamental frequency to control an AC source, and the DC interface of the renewable and energy storage is provided through a power balance equation. Dynamic average models have several limitations as they do not represent the high switching frequency transients, converter losses and harmonics. They neglect the neutral point dynamics for multi-level converter topologies, their switching functions, and block and deblock operating states of power converters. These models are more suitable for dynamic simulations of large grid networks integrated with a large number of multiple renewables and distributed resources. In the dynamic PQ source model representation, the model can be further simplified by neglecting the dynamics of the distributed generation source, the power electronic converter, and the DC bus. These models are suitable to do power system injection studies, where there are a large number of renewables and energy storage devices on transmission and distribution networks. The RTDS has several available converter models for renewable and energy storage applications to represent fully switched firing pulse models, switching function models, average value models, and dynamic PQ source models. In addition, the RTDS has very detailed and accurate control models to generate the high switching frequency for firing pulse-based converter model systems. The RTDS library also has available models for wind turbines, the PV arrays, lithium-ion batteries, an extensive library of machine models for energy storage and renewable applications. In this next section, energy storage case demonstrations will be included with a brief discussion of the cases that will be described and demonstrated. The first case is a microgrid system that includes a battery, a flywheel, a wind, diesel generator, and PV. The microgrid can be operated in grid-connected and islanding mode. The microgrid can be resynchronized back to the grid by using several control systems, including a switch capacitor bank, to maintain the resynchronization voltage and phase angle and frequency within the specified limits for reconnection back to the grid. The second case that will be described is a 300 megawatt variable speed doubly fed induction machine pump storage unit. The demonstration will include showing how the pump and turbine controls regulates the speed and gate position in pumping and generation mode. The demonstration will show the grid side converter controlling the DC link voltage, while the rotor side converter controls the machine power and speed in generation and pumping mode. In this section, a real-time demonstration of a microgrid with a battery, a PV, a diesel, a wind, and flywheel renewable and distributed energy resource will be discussed. The microgrid has very short transmission lines, less than 5 kilometers, so a pi section model are used to represent the transmission lines in the microgrid. The sequence data for the transmission line can be entered in the parameter tab of the pi section model. The microgrid has 7 loads. There are 4 fixed loads and 3 dynamic loads, representing the changing loads in the microgrid. The battery uses a lithium-ion battery model to represent the charge and discharge operation of the battery in real time. The Rcds battery model allows to enter the number of cells in stack and the number of parallel stacks to scale the power out of the battery. The battery model can represent one of 2 options. The mean Recon-Mora model focuses on modeling the electrical behavior of the battery, namely its voltage current characteristics. In this model, the battery lifetime modeling, which will describe long-term battery behavior such as self-discharge, is not considered. In addition, the thermal dependence of the circuit parameters, the thermal dependency of the circuit parameters are not included in this model. The second model is the Fourier-Cirello-Gazzouri-Jacqui model. This allows the temperature dependency of the parameters to be represented in the battery. The state of charge of the battery can be modeled. And can be monitored in real time. In the battery control system, in grid connected mode, a DQ current control loop in power control is used to control the battery grid currents. A PI control is used to regulate the error for the D-axis current reference and the error for the Q-axis current reference in order to limit the battery AC side currents. When the microgrid is islanded, the battery switches over to a droop controlled mode in order to maintain the power balance in the microgrid. For the flywheel storage system, the grid side converter controls the DC link voltage in charge mode, while the rotor side converter controls the machine torque and speed. The rotor side converter and the grid side converter topologies are 2-level back-to-back converter voltage source converter topology. The firing pulses are generated with the sinusoidal pulse width modulation. Typically, for permanent magnet synchronous machine drives, the machine side control is based on the field-oriented decoupled current control, where the rotor flux is aligned with the D-axis. The D-axis reference current is set to 0, and the Q-axis current controls the torque and subsequently the speed of the permanent magnet synchronous machine. In discharging operation, the machine side control controls the permanent magnet speed, and the grid side control controls the DC bus voltage. In charging operation, the machine side control controls the DC side voltage, and the rotor side control controls the permanent magnet rotor to a constant charging speed. The RTDS is compiled once the draft simulation case is built. The distribution of the components in the draft simulation case is shown in the Processor Assignment tab. The DERs and the renewables are solved in the small time step sub-step simulation environment of the RTDS, and this requires its own processor core on the Nova Core unit. Hence, fully switched power converter models are heavily resource dependent, as shown by the processor assignment. The control system components in the microgrid are solved on one core, and the power system components as well as the network solution for the microgrid voltages and currents are served on their own core. The processor assignment requirements can be reduced by using switching function models to represent the operation of the converter without using the fully detailed switch converter models, which are heavily computation requirements. Next, we're going to see the real-time simulation of this battery system in the RTDS runtime so that we can get plots and meters and graphs in real time with the operation of this system. Let's look at the real-time simulation model for the microgrid. Currently, the microgrid is grid connected with the PV, the diesel, the battery, the wind, and the flywheel. There are fault controls for adding faults to the microgrid. There is a load shedding control to maintain the frequency of the microgrid. There are synchronization controls for reconnecting the microgrid after it's islanded back to the grid. The switch capacitors to maintain the voltage limits to reconnect the microgrid to the grid. There's flywheel controls. There's battery controls. There's the diesel generator controls, the solar control, the wind control. There are meters to monitor the bus voltages, to monitor the power in the grid. Currently, the microgrid is grid connected, so any excess power generated by the DERs is sent to the grid. Let's see what happens when there is a step change in power when the microgrid is grid connected. The excess power demand from the load is supplied by the grid. The real-time simulation updates is coming on the computer, which is running at a much slower rate than the real-time simulation, but we can actually see the real-time updates of the meters. Now, when the grid is islanded, The microgrid picks up the power loss from the grid and maintains the power balance. If the flywheel is set to charge mode, the diesel generator, the battery, the PV, and the wind pick up the excess power from the flywheel changing to charge mode. If there is a reduction in the PV power output, it will be picked up by the droop-based response of the battery and the diesel generator. With the flywheel now in discharge mode, with a reduced PV output, the power balance is still maintained in the microgrids to supply the loads. If there is a reduction in the wind output, the wind speed, the battery, the diesel, and the flywheel pick up the excess power loss from the wind, and the grid, the microgrid supplies the loads. To reconnect back the microgrid to the main grid, a reclose signal will be issued. To make the voltage of the microgrid to be within the criteria of the synchronization voltage of the grid, switch capacitor banks are enabled to bring the angle difference to a set criteria. Then once the microgrid phasor aligns with the grid phasor, the microgrid will be reconnected back to the grid. So now we can see that the microgrid has synchronized with the grid and it's back to grid connected mode. In the next runtime simulation file, we're going to see the operation of a pumped storage hydro system running in real time on the RTDS. A variable speed pumped storage simulation model will be described. The configuration of this model uses a doubly fed induction generation system connected to the grid through a back-to-back two-level voltage source converter. The rotor side control of the variable speed defig uses the stator flux orientation, where the rotor current vector is oriented into a reference frame with the stator flux. The real power and the machine torque can subsequently now be controlled by the Q-axis rotor current vector, while the reactive power can be controlled by the D-axis rotor currents. The rotor side control uses a fast power control in generation mode and a fast speed control in pumping mode. The rotor D-axis currents can be set to control the stator reactive power by regulating the stator bus voltage. Typically, This current is set to 0 to minimize the rotor AC side currents. The stator flux angle is estimated using a phase lock loop, using the stator voltage equations in the stationary rotor frame. The grid side control uses the grid voltage orientation, where the D-axis current controls the DC bus voltage and the Q-axis current regulates the reactive power. The grid side D-axis current can be set to control the react power by regulating the grid bus voltage, or set to 0 to minimize the grid side AC currents. The pump and turbine control regulates the water flow in generating and pumping mode by adjusting the gate position. In this simulation case, the generation and pumping modes operation for the pump storage units are modeled separately. This is the turbine model for generation mode, and this is the pump model for pumping mode. This is the gate model for regulating the water flow through the pump storage, and this controller determines the speed and power reference for a given water head and set reference power points. The real-time simulation operation of the 300 megawatt variable speed pump storage simulation model will be demonstrated. The configuration uses the doubly fed induction generator connected to the grid. The back-to-back converters have a grid side control for regulating the DC bus voltage and a rotor side control for regulating the defig power and speed in generation and pumping mode. The control of the grid side parameters can be modified in real time to tune its operation. The control of the rotor side control can be also modified in real time to tune its operation. The real-time updates of the meters for the power, the bus voltages, the grid, and turbine power are provided in the runtime simulation model. In generation mode, the stator power is controlled by the rotor side converter, and the defig speed is controlled by the governor, which adjusts the gate position. The power flow in generation mode is from the defig turbine to the grid. The step response of the stator power to a step change in the power reference set point when in generation mode will be demonstrated. The fast power control in generation mode is controlled by the rotor side decoupled currents in the stator flux orientation. The stator flux estimated from the phase lock loop allows the stationary equations in the reference frame to set the new reference of the stator power. The power control is able to set the new power reference set points in generation mode. The operation of the pump storage system in pumping mode will be demonstrated. In pumping mode, the D-fix speed is controlled by the rotor side converter. The power reference set point is used to determine the governor output to adjust the gate position. The power flow is from the grid to the turbine. The D-fix response to a step change in the power set point will be demonstrated. The fast speed control of the rotor side converter control adjusts the speed to the new set point reference. The variable speed operation in turbine mode, generation mode, in pump and pumping mode has been demonstrated, showing the response to a step change in reference points in generation mode and a step change in the power reference set point in speed control mode. The controller is shown to be able to regulate the power and the speed with fast response in generation and speed mode. This concludes the demonstration for the variable speed pump hydro system.
Hello, everyone. I hope you can hear me okay. Thank you so much for your attention during this webinar. I know it was a little bit longer than they normally are, but we still have some time to do Q&A today. I wanted to start off by apologizing for the video resolution. We're just looking into why or how that happened, but we will be emailing out a link to the presentation file and to a higher resolution video. So if you're interested in rewatching that demonstration where you can see the plots better, you'll be able to do that. We've had a couple of questions about the sample cases, so I wanted to address those first. The sample cases are indeed available in Rscad Fx. So if you are running FX, we've updated the folder name. It's called Example Cases. And folder number 5 is called Energy Storage Systems. And that's where you can find the cases we're talking about today. So there are 3 different battery system cases. We have 2 different flavors, implementations of the lithium-ion battery. One is the Rincon Mora, and the other is the Huria Serralo model. Sorry if I'm butchering that name. And then we have the flywheel and pump storage system cases and the PEM fuel cell case. And that fuel cell case is quite simple. It has the fuel cell stack connected to a 2-level converter model that is implemented in the small time step environment. And then it just has a transformer and a source. And that source could be replaced with a more detailed AC network. Okay, let's see if we can hear Ani. Ani, is your audio working? Okay, maybe we do not have Ani with us. Ani, if you can try adding your audio back into the scene, hopefully we can get that working. In the meantime, I will address some other questions.
Hello, Katie. I can hear you.
Hi. Ani, we have some questions about grid forming control. And I thought it might be good if you wanted to comment on this. Basically, the question is about whether grid forming control has been implemented for our converter models and the various challenges of running grid forming control.
Currently, we don't have a sample case on grid forming controls, but you can modify the existing example cases with our control systems, and that's we can make grid forming cases available to interested users. It's just a modification of the control system models. So yeah.
Yeah, so if that's not clear, the controls aren't really inherent to the converter models. They can be implemented by the user using our controls component libraries. I think the challenges that Ben was bringing up in the Q&A, talking about how a grid forming inertial control needs to constantly exchange energy with the grid, maintaining its voltage angle reference and releasing energy to achieve that relative to the defined inertia. I'm not familiar with any customers that have done extensive work with this, but it is interesting. So we will look into that. And when we release our Q&A document, we might be able to comment a little bit more on that. Similarly, we have a question about using a nonlinear controller instead of PI controllers for the battery model. And yes, you can definitely implement a nonlinear controller, again, using the controls components in the Rscad library. There is a question about conducting studies with the RTDS over a 24-hour period. And Bruce Rigby had touched on that in the chat. Yes, the RTDS simulator is designed to run 24/7, so you can definitely run longer studies. Okay, just taking a look at our other question here. Are there any plans to add other battery models than lithium-ion batteries to the Rscad library in the future? Ani, did you want to comment on that?
There are no current plans to add future battery models, but we've definitely noted this down if there is an interest for different kinds of battery models as opposed to the lithium-ion battery.
Okay, great, thank you. Yeah, and if you're a user of the RTDS simulator and you have a particular model that you're interested in using, you can contact our support team. And we can have a discussion about whether that model might be something that we can bring into the Rscad environment for you. Here's a good question, Ani, that maybe you can get into a little bit. From a simulation point of view, what is the difference between the flywheel and the pumped hydro systems? So I think that's a question about the differences in how those systems are implemented in Rscad, how they're modeled. Mm-hmm. And do both sources have the possibility to increase or decrease ramping capacities?
Yeah, so the major difference between the two simulation examples, first of all, is even from the technology. So in the simulation case, the pump storage case is a doubly fed induction machine for 300 megawatts. And the flywheel is a permanent synchronous machine for 2 megawatts. So, that's quite a difference. And the control systems of the flywheel and the pump storage are different. The flywheel follows conventional hydro controls where there is a speed and gate governor control. So that transient operation of the pump storage is different from a flywheel that uses machine side and grid side control for fast speed and power regulation. So there are two different technologies, there are two different machine models, and there are two different control systems. So you had the second question. What was the second question you had mentioned?
I think it is about ramping capabilities, whether you can increase and decrease them.
Yeah, you can ramp up the set point references. That's what we showed up in the demonstration. So you can ramp up the speed reference. You can ramp up the power reference. You can run our simulation models for 24 hours. Yeah. So.
Excellent. Thank you. We have a few more questions that have been coming in here. First, I do want to mention we are currently working on developing grid forming control examples. So in the near to medium future, we should have some sample cases related to grid forming control. So hopefully that's helpful to you, Ben, and anyone else who's curious about that. We have another question. Oh, go ahead, Ani.
Yes, I was just about to mention that, like, Ben had some very good suggestions on some of the technical challenges with operating grid forming controls with battery storage, and that's something that we can note down when making such examples. We like to get feedback on what kind of examples would be relevant technically to what users want to model with the RTDS.
Excellent, thank you. We have a question about black box type functionality, whether Rscad provides a black box functionality so that vendors can provide their controller models, for example. And yes, we do have a black box functionality. Basically, you're able to lock and encrypt the contents of a hierarchy box so that the box can still run, but the contents are not accessible. So we do now have a black box capabilities with Rscad Fx. We have a question about transmission lines. In the sample case, renewables were connected by short pi section line models. Could we also use frequency-dependent line models in conjunction with the components in the RTDS? Ani, do you want to talk about that a little bit?
Yes, you can use frequency-dependent line models. We have those models available in the RTDS. In the presentation, we do note that there is a trade-off between the complexity that you use in these models with your required processor capabilities. So the more detailed and complex models that you require, depending on what transients you want to capture, you would require more, processing speed to use this, frequency-dependent line models. For studies where the details of this frequency dependence of the line is not required, then you can use the pi section models to do the simulation. So yeah, we do have those models available if that's what you want to include in your simulation.
Absolutely. Okay, I'm going through the questions here. I think we have touched on all or most of them. And if we haven't touched on your question, it will be answered in the Q&A document. And there were a couple questions that were specific to people's simulation cases. You can always contact support at rtds.com if you have questions about your simulation case in particular. I want to thank you, Ani, for being with us today and for your presentation and demo. And thank you so much, everyone, for attending. I hope to see lots of registrations for our upcoming webinar on the universal converter model. That is a big step change in power electronics capabilities for the RTDS simulator, and you can find the registration link in the more information box. So thank you so much, everyone, and I hope to see you next time.